And what I would like to do to start with today is I gave you 2 exercises, or at least 3 exercises the last time. I will start with the 2 first exercises. So I will work it out that you see how you can obtain the solution by Fourier transform methods. But I also will show you in one of the examples how that problem that you're solving, how that is related to the Green's functions. Yeah, so I will integrate actually what we're now doing in chapter 10 of Fourier transform methods, again back to the chapter 9 results of Green's functions for the Laplace equation. And remember, one of the exercises you had to make was this exercise. Laplace u is 0, y was positive.
I don't know what to refer to and what I have to tell them. I have no idea. Is it clear now?
And you had to solve this problem where you had in the point x is y is 0, you had a delta function. And you remember that if you're going to construct a Green's function, then also a delta function was involved. Yeah? Okay, but first we are going to construct the solution. So let's have a look at the problem. Here we have y, here we have x, and this is our domain of interest. And here in the origin we have a source. And we look at the stationary heat problem, for instance, and we have a source at the origin, and it's producing heat in a continuous way. Yeah? Unit heat is produced continuously. Yeah? And we look at the stationary solution, and actually what we ask ourselves is, what is the temperature due to that source? Yeah? Okay. So what you're going to do is you're going to look at the Fourier transform of your PDE. And you're going to look at the Fourier transform of your initial function. According to the definition, you can only Fourier transform those variables which run from minus infinity to plus infinity. Well, the only variable that is running from minus infinity to plus infinity is x. So what we define also is that big U of omega ny is actually defined to be 1 over 2 pi integral from minus infinity to plus infinity u xy e to the power I omega x dx. Yeah? So that's the definition we use. Okay, so we first have to Fourier transform the Laplace equation, which is the Fourier transform of uxx plus uyy. That's equal to the Fourier transform of 0, and that obviously is 0. Yeah. And then I know that the Fourier transform is a linear transformation. So it's the Fourier transform of uxx plus the Fourier transform of uyy. And if you Fourier transform the second order derivative with respect to x, you can still look here on this blackboard. We did that yesterday. The second order derivative, that is minus I omega squared times the Fourier transform of that function. So we will get minus I omega squared times the big U of omega and y. That's this transform. Here I have to transform uyy with respect to x. So the derivative with respect to y can be taken out of the integral. And I will get over here the second order derivative with respect to y of big U. Yeah? Plus u yy omega y is equal to 0. So here I transformed my PDE with respect to x and the Fourier transform. Then I have to Fourier transform my initial condition. Well, what do I get? The Fourier transform of u x0 will be u, big U, omega 0. And that should be equal to the Fourier transform of the delta function. Well, look at the table. The delta function is 1 over 2 pi times e to the power I omega x0. In this case, x0 is 0, so I will get 1 over 2 pi. Yeah? So that's 1 over 2 pi. And now I have to solve this PDE subject to this condition. Okay, let's look at the PDE. PDE for big U omega y. That PDE reads U y and then minus omega squared big U is equal to 0. What are the solutions of this PDE? Yeah, you can look at it as an ODE. So I will immediately find solutions e to the power plus omega y and e to the power minus omega y. Yeah, so this equation has solutions. This equation has solutions e to the power omega y, e to the power minus omega y. And then we have a problem. Because we know that temperatures and physical quantities are always bounded. And if you look at e to the power omega y is positive for our problem. And omega can be positive or negative, because omega is running from minus infinity to plus infinity. So that means that if omega is positive and y is positive, then this will blow up if omega starts to increase and y starts to increase. Similar here, if omega is negative and y is positive, then it also can blow up. So out of these solutions, we should only take the bounded solutions. And how can we find it? Bounded solution. Then we should take only the parts that are bounded, and then leads to e to the power minus the absolute value of omega times y. Then I for sure have bounded solutions. How many do I have? Well, for each omega I have one. I add them up, yeah, the superposition principle, so I can say, okay, the general solution of this problem, which is bounded, is a constant c omega times e to the power minus omega times y. So that's my general solution. And this general solution has to satisfy, for y is equal to 0, it has to be 1 over 2 pi. So we continue. U omega 0 is 1 over 2 pi, and then it follows that my u omega y is 1 over 2 pi e to the power minus omega y. And this is my solution. Yeah. Okay, so it's quite easy to solve the problem in the omega y domain. And now I have to go back, so now I have to look at the inverse. The inverse transform. What's the question? No question, okay. What's the inverse? Yeah, then I have to compute an integral from minus infinity to plus infinity of this function, 1 over 2 pi, e to the power minus omega y, e to the power minus I omega x dx. Sorry, the omega. Yeah? And then the question is, can I compute this integral? Well, to compute this integral, I first have to get rid of these absolute values. So I split up this integral into to the part from minus infinity to 0, 1 over 2 pi e to the power plus omega y times e to the power minus I omega x d omega plus the integral from 0 to infinity 1 over 2 pi e to the power minus omega y e to the power minus I omega x d omega. Yeah, so I split the integral up into two parts, getting rid of my absolute values. You all agree? Yeah, something is not clear, pose your question. Okay, so now I can compute the primitive because I can take together both exponentials. Yeah, I can write it down also for you in that step. Minus infinity to 0, 1 over 2 pi e to the power omega times y minus ix d omega plus the integral from 0 to infinity 1 over 2 pi e to the power, then I have minus omega y plus ix d omega, and you all know how to get the primitive of an exponential function. That's again an exponential. And then I will find the following as a primitive, and then I will get 1 over 2 pi y minus ix, and the other one will give me minus 1 over 2 pi I plus ix, and then I have to substitute here times e to the power omega y minus ix, and here e to the power minus omega y plus ix, and then between, well, this has to be computed between omega is minus infinity to 0, and this has to be computed from omega is 0 to infinity. Yeah? Okay. Substituting the upper bound for omega 0, this gives me 1. So I get 1 over 2 pi y minus ix. And if I substitute omega is minus infinity, what is the outcome? Is it 0? Why is it 0? Yeah, the real part is y. Y is positive. Infinitely with a minus sign times something positive gives you e to the power minus infinity as a real part. That goes to 0. The imaginary part is not important because that's just a bounded function. That's a cosine and or a sine. Yeah? So that gives me 0. So the lower bound gives me near 0. Then the other one. If I substitute the upper bound, what do I get? This is the real part, which is positive. E to the power minus infinity again. That's the real part. So that goes to 0. The lower part will give me just 1, and then with a plus sign, so I will get 1 over 2 pi y plus ix. Well, my solution, of course, should be a real function. So I have to get rid of somehow my function ix and over here. So I have to add them. And how do you do that? Well, you just multiply this one with y plus ix and this one with y minus ix. So you'll get y plus ix over 2 pi. And then you will get over here y squared plus x squared. Yeah? Denominator and the numerator are multiplied by y plus ix, and similarly I multiply here the numerator and denominator by y minus ix, and then I get plus y minus ix over 2 pi y squared plus x squared. And in total I will get 2y. This one cancels with this. I can divide by 2, 2y over 2. And so I will find y over pi times x squared plus y squared. So that's my solution. A nice solution. So if I have a heat source over here, or an impulse in my temperature, in this case, an impulse in my temperature, then the temperature distribution is given by this formula. And you can nicely plot it if you wish. Okay. If this is clear for everyone, you will see that you can use this table. Yeah, and it goes quite smoothly. Now we should pose ourselves a question. Could we also have solved this problem in a different way? Because in chapter 9 we had Green's functions. We had Green's second identity. What was it saying? Well, if you take the integral over your domain, u Laplace g minus g Laplace u dt, that was equal to the integral over the boundary of my problem of u dg dn minus g du dn. And now I constructed a solution. So I now know not g, but I now know u. What do I know? I know this one, that's 0. I also know in this formula my u on the boundary. What's the u on the boundary? The delta x, eh? The Green's function has to satisfy the same homogeneous conditions. So what's the g on the boundary? 0. Yes. What do we know further? What do we know about Laplace g? If I have a Green's function, that's usually a delta function, eh? Yeah. Okay, what do we know? What do we know further? This is n. So I have to compute the boundary integral, this boundary integral, and that's actually the boundary integral that is running in this direction. And then here at infinity, it goes to infinity and goes back again, comes back, yeah, and it's done in that way. And that's the integral over my boundary, where the dotted line here is at infinity. Yeah, but that's how I go through my boundary. So this is actually an integral from minus infinity to infinity. So I can write for this the integral from minus infinity plus infinity of delta x times the GDN, and the GDN is minus dg dy. You agree? because the GDN, that's in the negative y direction. So the GDN is minus the GDY. And where do I compute my G? Well, that is in the point x0, x0, y0. And then I have to compute here the x. Okay. I can also compute this integral. That will give me only x0. Then I have to look at the integral that I have at the end. What do I know? It's delta x times this. What's the outcome? Minus? You agree? Oh, that's nice. But I also know my solution, because I computed it here. I know my solution u. Uxy was this. So u in the point x0, y0, that's equal to y0 divided by pi over x0 squared plus y0 squared. And we also know that we have a symmetry property that you could interchange x with x0 and you could interchange the y with y0. It gives you the same thing, eh? So the GDY is also the GDY0. Yeah, you agree? So I can integrate this, and then I will find my G, which will be 1 over 2 pi logarithm x0 squared plus y0 squared. You agree? So if I integrate, there should be a plus because I have y minus y0. Yeah? So the GDY is minus GDY0. Yeah? And because I always have y minus y0 squared. Okay, so I find this. Hey, that's a formula I know. Because if I use my Green's functions, and I have my domain here, and I have that G is 0 on the boundary, and I have here a point x0, y0, and I had to compute the Green's function satisfying G is 0 on the boundary, and I have here a plus charge, then I should use the image here with a minus 1. Yeah? And if you write down then the Green's function, it turns out to be 1 over 2 pi logarithm x minus x0 squared. Yeah, this form, minus 1 over 2 pi logarithm x minus x0 star, where this is x0 star. Yeah? Now we should put this formula. Well, I integrate here with respect to y0, so actually if I do it correctly, I should add here still another function which depends on x0. Yeah? So you have an additional term over here. But the interesting thing is that you see that you are reconstructing actually what you have there. And this is the Green's function at point 0, 0. And if I compute here the point 0, 0, I will just get here 1 over 2 pi logarithm x0 squared plus y0 squared. The same as here. Yeah? So you see you're actually doing the same thing. Yeah? And with this constant that you have here, you make again the boundary equal to 0. Is it clear for everyone? So now you see what the relationship is. Well, we have here a Fourier transform. We directly compute the solution. We also have been able to compute it in this way. And if I now use this Green's function, yeah, then you have to substitute in this formula your Green's function. Given Laplace u0, put here the delta function. And then you can compute it again, and then you get the same answer as what we found here. Yeah? And so it fits nicely. So you can also do it in another way. Solve a very special problem. And I solved here the problem with only here a delta function here. Well, it doesn't matter what you solve actually. Yeah, but you can reconstruct then from that the Green's function. It's clear for everyone? Yeah, you see coming back the logarithm here. Yeah, and we know that the Green's function has this structure. And for the point x is 0, which we found here, point 0, then we should take, in this case, x is 0, then this is just a constant. And that's the constant that I have to do here with that integration. Yeah? So you see exactly the same formulas coming back. Yeah, because here actually I should have g0, x0 for comparison. Yeah? And then this is a constant, and this is logarithm x0, which is the logarithm of this. Yeah, clear for everyone? Okay, now we're going to the next exercise. And that exercise was, that's already in section 10.5. This problem you have to solve. In the book they have several sections on Fourier cosine transforms and Fourier sine transforms. I never treat that because you can do it in another way, much more efficient. Moreover, in physics you usually have more difficult boundary conditions, and then a Fourier cosine transform and a Fourier sine transform really do not work. Yeah, so you always have to go back to what I'm going to do. We earlier solved the problem ut is equal to kuxx, ux0 is fx, and we solved that problem on the infinite domain. Yeah, that's what I started with yesterday. And then we found that the solution uxt, that was 1 over the square root of, well, what was it? Yeah, this was your solution. If you look at this solution on the infinite domain, then you immediately see that this solution satisfies the PDE. Yeah, because the PDEs are the same. And if I take t equal to 0, then we are satisfying also this condition. But if I look at this problem, fx is only defined for x positive. Whereas here, f is defined on complete interval. So if I look at this problem and I use this integral, then it satisfies the PDE and the initial conditions, but there is still something which is not defined. That is f for negative arguments. Yeah, you all agree? So we can say this formula satisfies, and if I call this problem problem star, satisfies the PDE star and initial condition star, but fx is not defined for negative arguments. Yeah, so there's still something that's not defined in that integral, although it satisfies the PDE and the initial conditions. But I here have an additional condition. I have an additional condition, u has to be 0 for x is 0. So that condition I can try to impose on this formula, and then most likely I will get my definition for fx for negative arguments. So let's try that. Still, we have to satisfy u0t is equal to 0. Okay, let's write down. 0 is u0t is the integral, the integral 1 over the square root of 4 pi kt times the integral from minus infinity to plus infinity e to the power minus x squared over 4 kt times fx dx. I just substituted x is 0. Yeah, then I get this condition. Okay, this integral, which here depends on fx and x squared, has to be 0 and still this has to be 0, and the only thing that is not defined is this function fx for negative arguments. Yeah. What do I see? I have here an integral around the symmetric integral around the point x bar is equal to 0, and whatever the fx is for positive values, this integral should give me something that is 0. What is the property of this function? E to the power minus x squared. That's a symmetric function, and that's also what we call an even function. Yeah. So this function is even in x. I multiply that with the function fx, which is only defined for x positive, and for x negative it's not yet defined, but the integral should be equal to 0. What should be the property of f to get this always 0? If it's on one side up, it should be on the other side down. Yeah? And vice versa. So that means that the function should be odd. Yeah, so from this it follows f minus x should be equal to minus fx. It should be odd. Yeah? Make a picture like this. If I have here x is 0, then if it's here up, it should be here down. Then that integral over f from minus infinity to plus infinity will be 0. So all things that are here up or down should be the other way. So I should have this. Have we seen that earlier? Well, think of your Dirichlet boundary conditions and your Fourier series. If you have a Dirichlet condition, so u is 0 on the boundary, then you call a Fourier sine series. Sine functions are odd functions. So all functions are expanded in odd functions. Dirichlet condition, of extension. So that remains the same. So without doing any computations, you might now say, if I would like to solve this problem, my solution is this, where f is an odd function. Okay. Yeah, it's odd in x with respect to the argument x is 0. Okay, but I can rewrite this uxt is 1 over the square root of 4 pi kt times, now I'm going to rewrite it as an integral from minus infinity to 0 e to the power minus x squared over 4 kt fx dx plus the integral from 0 to infinity e to the power minus x bar squared over 4 kt times fx dx. That's still my solution. I only split up the integral. And what I'm now going to do in this integral on the interval minus infinity 0, which is actually not belonging to the domain I originally have, I'm going to put over here x bar becomes minus x bar. And then this integral becomes the integral from infinity to 0. My x bar becomes minus x bar, so I will get minus x plus x bar squared over 4 kt times f minus x times the d of minus x bar. Yeah, so I replace x bar by minus x bar. That's the only thing I do. And then the other integral I still write down. So I have the integral from 0 to infinity e to the power minus x bar squared over 4 kt fx dx. So I change nothing. And now I use the fact in this integral that f minus x is equal to the minus of fx. And of course this is minus, yeah, so I get a minus here. And I switch this integral. So I have 3 minuses. Yeah, this minus due to the switch, here a minus and here a minus. So I'm left with a minus. Yes? Okay, so I can rewrite the solution. uxt is 1 over the square root of 4 pi kt times the integral from 0 to infinity. And then I get here the expression e to the power minus x bar squared over 4 kt minus e to the power minus x plus x bar squared over 4 kt fx dx. You agree? Yeah? So what I see is that my u is given by this formula. It's defined nicely on the interval 0 infinity. And I can also see what my Green's function is, because my Green's function, g xt x bar 0, that's equal to 1 over the square root of 4 pi kt times e to the power minus x bar squared over 4 kt minus e to the power minus x plus x bar squared over 4 kt. And here I have my Green's function. And later on in chapter, well, what is it? We're now in chapter 10, so that will be in chapter 11. Then you will see that the Green's function for the heat problem is 1 over the square root of 4 pi kt minus t0. And here already you have your x minus t0. Yep. Okay. Is this also clear for everyone? And some of you already did something on Fourier sine transformations and Fourier cosine transformations. This is much simpler. Yeah. And you only have to know this. No Fourier cosine table, no Fourier sine table, which is only applicable to that very special class of boundary conditions. And you can immediately do it from this. Yeah, and what you will see if we're going to do the workshop, some of you in the workshop that will join one of my groups, we are going to look at the wave equation, and then also we have boundary conditions, more difficult boundary conditions, and we're going to do reflections of waves. And then we use the formula of D'Alembert, which is in fact a similar representation as this, because this formula you might see as a formula of D'Alembert. Yeah? The formula of D'Alembert was quite simple. You had a wave traveling to the left and to the right for a wave equation. And you've got a half fx plus t with a half fx minus t plus 1/2 times the integral x minus t to x plus 2. Yeah, and then g, yes. It's something similar. Yeah, so you might call this the formula of D'Alembert, but then for integral. Yeah, and you can do the same things with reflections. Also, this is a reflection due to your Dirichlet condition. Yeah, this is how the heat is actually reflected due to the boundary condition. Clear for everyone? Okay, next problem. That's already an example in section 10.6. Yeah, if you look at the book, then you will see in section 10.5 and 10.6 there are lots of examples. Yeah, I cannot think of them, of course, all of them, but if you have a problem and you want to see how it works, look in those sections, 10.5, 10.6. Yeah, I will take out a few. And one of them is the following. Ut is equal to k uxx plus uyy, and I will look at this problem. So now I have an infinite two-dimensional space. An infinite two-dimensional space. Here I had a one-dimensional problem. Over there I have a two-dimensional problem. If I know how to solve this problem on the infinite domain, I can look at half spaces. I can look at quarter spaces. Yeah? Because of these nice properties with reflections. So if I have a half space, let's assume, it's in between brackets, that I only assume that this is my region, and here, for instance, I have u is 0 on the boundary, then I know that I have to extend in the y direction all my functions as odd functions. And then I have again an infinite domain. So then I have to solve this problem. So if I can solve this problem, I can solve this problem. If I have as a domain, for instance, this, and here I have u is 0, and for instance here the u the end is 0, then I know that in this direction I should extend my functions as odd, and in this direction as even. And then I obtain again this problem. So if this function, for instance for this problem, is extended in y as odd function and in x as even function, then I'm solving actually that problem, but the solution is given by this formula. Yeah, where f is odd in x and, even in x and odd in y. Yeah, so if I can solve this problem, these problems are relatively simple. Yeah, and that's what I do in the book. First I solve this, and then, yeah, they make it a little bit difficult by looking at Fourier cosines and Fourier sine transforms. Yeah, but you don't have to do that. Okay, so then the question is, can we solve this problem? Here we have x and y, and x and y are running from minus infinity to plus infinity. So we might transform the problem with respect to x. Yeah, so let's do that. So I have to Fourier transform. I have to Fourier transform my PDE. I have to Fourier transform my initial function. Okay, let's do that. PDE and initial condition. Then I will get over here this. K times the second order derivative with respect to x, I Fourier transform with respect to x, so I will get over there k times minus I omega 1 squared u. And here I have the derivative with respect to y. I don't do it with respect to y, only with respect to x, so I will get over here plus k times u by y. And the initial condition becomes u omega 1 yt is the transform of my function f x y with respect to x, so I will get over here an f omega 1 y. Can I solve this problem? Well, it's a heat equation with ut and then uyy, and I have a u. So that problem is even more difficult than this problem that I solved earlier. But I can also, of course, Fourier transform this problem with respect to y. Yes? So let's do that. U omega 1 omega 2 t is 1 over 2 pi, integral from minus infinity to plus infinity, so now I also transform with respect to y. Then this PDE becomes u t is equal to, well, I can compute that, that's of course k times minus omega 1 squared u, and this becomes plus k times minus omega 2 squared u. Yeah, you agree? And my initial condition, that's just u omega 1, omega 2, 0, I should have put there 0, yeah, that should be 0, is equal to f omega 1, omega 2. And what you do in practice, usually you do that in one step. So I did it now in 2 steps, but if you have variables that are running from minus infinity to infinity, you usually say, I do this in 1 step, and then you write down the following. Then you write down the following. U omega 1 omega 2 t is equal to 1 over 2 pi squared integral from minus infinity to plus infinity of u x y t e to the power minus I omega 1x e to the power minus I omega 2y dx dy. So you can also do it in 1 step. Yeah? And this is actually taking in 1 step what I did over here in 2 steps. Yeah, first the first one, then the second one. Yeah? So if you have a 3-dimensional problem, you immediately write down 1 over 2 pi cubed u x y z t e to the power omega 1, omega 2, omega 3 dx dy dz. Yeah? Because else you have to write too much, and mathematicians are usually lazy. Yeah? That's why we have so that compact form of writing things out. Okay, so now I have to solve the problem. Ut is equal to minus k omega 1 squared plus omega 2 squared times u, and u omega 1 omega 2 0 is f omega 1 omega 2. So I started from a problem over here, which was difficult. I don't know how to solve it. Yeah. After the Fourier transform, I arrive here at a problem. This looks like an ODE, and I can solve that. So I go from an unsolvable problem to a solvable problem in another domain. So I can write down the solution. U omega 1 omega 2 t is equal to a function c omega 1 omega 2 times e to the power minus k omega 1 squared plus omega 2 squared times t. Yeah, that's the general solution of this PDE. It's integrable as an ODE, and then the constant depends on the variables to which I'm not integrated. And I'm not integrated with respect to omega 1 and omega 2. So the constant depends on omega 1 and omega 2. Yeah? Then I have this initial condition for t is equal to 0. If t is equal to 0, my u should be equal to f. So that constant should be equal to f. Use initial condition, and then you find that your u omega 1 omega 2 t is that function f omega 1 omega 2 times e to the power minus k omega 1 squared plus omega 2 squared times t. So this is my solution in the omega 1 omega 2 space. And then I have to think about the inverse. Yeah, so the Fourier transform, the inverse. How should we do it? Inverse twice, yes. Of course, we have to do it with respect to omega 1 and omega 2, because I have to go back to x and y. Anyone a proposal? If you look at how I did it here, I first transform with respect to x, then with respect to y. So now I will go back, and I will first take the inverse with respect to y, to get my function u tilde, and then use the inverse with respect to x to finally obtain this one. Yeah, so I will show you the steps. So inverse with respect to omega 2. What do I have to write down? So I will get u omega 1 y t, which is defined to be the integral from minus infinity to plus infinity of my f omega 1 omega 2 e to the power minus k omega 1 squared t, sorry, omega 1 squared plus omega 2 squared times t times e to the power minus I omega 2 y d omega 2. That's the definition. Yes? So that's the definition of the inverse with respect to omega 2. Okay, so this is an integration with respect to omega 2. So omega 1 is not important. I can take that out if I wish. So I can rewrite that as e to the power minus k omega 1 squared times t, integral minus infinity to plus infinity, f omega 1 omega 2, e to the power minus k omega 2 squared t, e to the power minus I omega 2 y d omega 2. I see that I have a product of a function of omega t 2 times this exponential. Can you give me what is that integral? Can you tell me? If the omega 1 is not there, that's not important. I have f omega e to the power minus k omega squared d omega. I compute the inverse. So I have a convolution integral, f omega times g omega. Yeah? F times e to the power minus k omega t. So I have a convolution integral. So I will get back something, 1 over 2 pi, integral from minus infinity to plus infinity. I have the original function belonging to that f, and that will be f tilde omega 1, and then I have as a variable y bar. Yeah? And then I should look at my g omega, and that's that exponential e to the power minus k omega t, that is this one. Yeah, sorry, this one. This one. Yeah? With alpha in this case equal to k times t. So we will get back something like this. So I will get back over here the square root of pi over kt times e to the power I get this, yeah, because I have the convolution integral and I should have f of y minus y bar. Yeah. Yes, you agree? Yeah. Yeah, that's clear for everyone? Put it a little bit more like this. Yeah, here convolution. F y bar y minus y bar. Okay. So I now use the inverse transform to obtain this. And of course I can make it simpler by rewriting this as e to the power minus k omega 1 squared t. And then I can take this together to write down 1 over the square root of 4 pi kt. Then you recognize immediately what we have. Times an integral from minus infinity to plus infinity. F tilde omega 1 y bar e to the power minus y bar squared over 4 kt d y bar. And then immediately we recognize already part of the heat equation for the one-dimensional case. Okay, that was 1 over the square root with t and then that integral. But now I still have to transform back with respect to the variable x. Yeah? So with respect to omega 1. I have to compute this integral, the inverse. Yeah, I have to go back for my omega 1 variable, back to my variable x. So I have to compute this integral, where u is given by this formula, or actually that formula over there. Okay, so let's substitute that in. So I have to compute the integral from minus infinity to plus infinity, then substitute that integral, 1 over 4 pi kt, e to the power minus k omega 1 squared t, and then I have an integral from minus infinity to plus infinity, f omega 1 y e to the power minus y squared 4 kt dy. And then the e to the power minus I omega 1 x d omega 1. Yeah, you agree? I just substituted in what u tilde was. That's the integral. Okay. Is equal to, well, let's take out 1 over the square root of 4 pi kt. And then let's have a look. I would like to integrate with respect to omega 1. So what I'm going to do is I'm going to interchange the integration. So I put at the end here an integral from minus infinity to plus infinity dy bar. Okay. Then I can take out, for sure, e to the power minus y bar squared over 4 kt. And then I have to write down an integral from minus infinity to plus infinity. I can write down the f with omega 1 y bar. Then I can write down e to the power minus k omega 1 squared t, e to the power minus I omega 1 x. and then I only have left the omega 1. Yeah, you agree? Yeah? Here I have only the integration with respect to omega 1. So I have to study this integral. What can we say about this integral? Omega 1, omega 1. Hey, convolution integral. Function of omega, function of omega. Convolution integral. What do I get in convolution integral? My original function f, small f, and to this function belongs z1. Yeah, so I'm doing the same thing again. So I can write down 1 over the square root of 4 pi kt times the integral from minus infinity to infinity e to the power minus y squared over 4 kt times, and then I get, well, start with this, so let's start with the square root of then here I have my convolution integral. And I get this. Yeah, you agree? Convolution integral. So I get 1 over 2 pi, convolution, the function f with the one that is translated, x minus x bar, the x, yeah, and then my dy. Okay, then I can take all things together. This becomes 1 over the square root of 4 pi kt, so I will get over here 1 over the square root of 4 pi kt squared. Then I will get a double integral, minus infinity, this. I will get f x bar, y bar, into the power minus x bar squared, minus y bar squared, divided by 4 kt. And then I get the x dy. So this is the solution of my problem. So if I give an initial temperature distribution at t is equal to 0, then in the two-dimensional space, the temperature distribution in time will be given by this formula. So it will spread out. Yeah, this is spreading out. This is spreading out, and this is how the amplitude goes down. Yeah? We saw that also in the one-dimensional case. So this formula looks much like a one-dimensional case. Only this is squared, and I have here the additional term with respect to y. You can imagine what the formula will be in R3. It will be this expression to the power 3, and then minus z bar squared. And here you see how you can use the Fourier transform method and how efficiently you can compute it. Yeah, and you cannot compute a solution with separation of variables or things like that. Using this formula, if you have boundaries, so a semi-space or a quarter space, you can just extend it as even and odd. Yeah, and then also you have your solution. This is clear for everyone. Yeah. Okay. So these are the equations in R3 and R2. Then an exercise that you can make, but that's for next week. Make exercise 10.6. Well, what is it? Use my glasses. 10.6.11 B. Yeah. And then, as an exercise, you might start to do it. But that's a rather difficult exercise. In R3, we are going to look at a function s, which is depending on x, y, z, and t. And the problem that we're going to look at is this function, minus c squared Laplace s is 0. And then we look at t larger than 0, x in R3. The initial conditions are Sx0 is 0 and Stx0 is the delta function. And you know that if you look at such a problem and you can solve it, then actually you are already constructing a Green's function. Use the Fourier transform. Use the Fourier transform method to construct S. And S is what is called the source function. What's happening? It's a problem in space R3. So look in this room. That's R3. It's a wave equation. So think of sound waves. And what are we looking at? Well, at time t is equal to 0, I have an initial impulse. What can that be? An initial impulse, I clap my hands. And then you get a sound wave through this region. And what you're then computing is actually how that sound wave is traveling through this space. And that's what you're computing over there. Apply the Fourier transform. And then you will encounter some problems. But try to do it, because you learn the most of the things that at a certain moment you cannot solve. Because then you know, oh, and then you learn really something. Yeah, so as soon as you are not able to continue, and others can explain that small step to you, and then you're learning a lot. Yeah? You don't learn so much if I'm explaining it completely to you, because then you don't have to practice. Try, and then you will see. Some students come further, but then at a certain moment they also cannot go further. Yeah, because you have to use a lot of analysis that you did earlier in your bachelor. Yeah, so you have to compute integrals. You have to look what does the integral actually look like. Can I use polar coordinates, spherical coordinates, whatever, to make the integrals more simple. Yeah? And that's actually the practice that you should get. And you learn the most when you cannot go on. Because then you learn. If you can go from, I can give you a very simple exercise. Yeah, and then you're very happy, I can solve it. But then you should ask yourself, did I learn something? Yeah? Actually not, because you knew already all the steps. Yeah, so it's actually a waste of your time, because you already could solve it. Yeah? Okay, we now have lunch. Then there is a conference the coming week, and we will be back here on Friday. That Friday morning we start with this problem. Yeah, so don't worry if you cannot find a solution. We will explicitly tell you how to tackle it. And actually what we're constructing here is the Green's function for a three-dimensional wave equation. And then we will still have 2 lectures on PDEs. That is on Friday next week and Saturday next week. And then we will tell you how you can use those Green's functions to solve problems with wave equations, and how waves, for instance, if you have a wall over there, then the wave is reflected. Yeah? How you can compute that reflected wave. Yeah, and there might be damping in the air, for instance, there might be damping on the wall, how you can do such problems. And then on Sunday there will be no lectures, and then on Monday we start with a workshop, and then Ferdinand Verhulst, Theo Dumankota, Fajar, Usomo, and we will have all 2 projects. On Monday morning we will explain to you, each will explain 2 projects to you, and that will be problems that are related to research. Yeah, so actually we will also tell you something about journal papers related to that, and what our PhD students did on that, and what bachelor and master students were doing on that problem. Then then you are allowed to choose a project, and then we will make it in such a way that each group has about 3 or 4 students. And those 3 or 4 students are working on one of those 8 projects. So we have about, 8 projects that will be done, and some groups will have 3 students, some other groups will have 4 students, yeah, on average, and they will work during Monday afternoon, Tuesday and Wednesday on those problems. Of course, we will be around, yeah, and we will help all the groups, but the group is actually doing that short research program. And that short research project, yeah, you can think about, well, I'm interested as group to study this. So you can also subdivide some of the problems to within the group. And someone is making nice pictures, someone is doing some analytical work, then he cannot continue, and then the others might help. We are also around, so we also might give you hints. Yeah, but we will show you how you can do research. Yeah? And the problems are really that we also don't know yet the answer. Yeah? Well, we have an idea what the answer might be, yeah? But we don't know exactly the answer. And then you see how you can do research. And the projects that I'm going to do are in some sense quite elementary. At least they look elementary if you know the solution. That's also what I also told you. That's as soon as you know the solution, okay, the problem is elementary. Yeah? But you can still do a lot of things, and we have journal papers related to that, and you can read the journal papers. They are usually written by my PhD students. Yeah? And then you can see in those journal papers, oh, I recognize here the averaging method, the multiple time scale method. I recognize here the Green's function. I recognize here the formula of D'Alembert. Oh, they use it like this. Oh, I didn't think of that. And that's how you do research, and that's how you write journal papers. Yeah? And that's of course going too far to write a journal paper after 3 days, but that's what we intend to do, that you get the grasp of the ideas, that you see that the things that we are doing are actually quite close to the research that PhD students are doing and scientists are doing. Yeah, so we are telling you, yeah, one step a little bit higher and you're already in research. Yeah, the problem that I gave you, what I said was a difficult problem, yeah, you cannot find the answer in the books. So we can write a journal paper on that. Yeah, and we did it also for circles and things like that. And if we have time to write a paper, but then you will see how close you are already to research. And posing a question to a teacher can be also the question that the teacher said, we don't know. Yeah, especially when you become a master student and you pose questions, then the teacher sometimes says, we don't know, then you are in the research field. Yeah, and that's the nice thing, and then you can think and then be creative, and then you find a solution, and then you can write a journal paper, present it in a conference, and so on and so on. And that's what a lot of people really like to do. Yeah? I like it already all my life. Ferdinand Verhulst is also an example. He's already retired for a long time. Yeah? In the Netherlands we retire nowadays at 67, so that actually you don't have a position at the university anymore, but still he's doing research. And we have a lot of older people that are doing that. Yeah? But you also have to like it, of course. It's more like a hobby, yeah? You can pay for it, it's nice. Okay, then also the group, when you have done the research project on, let's say, Monday afternoon, Tuesday and Wednesday, then on Thursday the group has to present their results to the whole group. So if your group, for instance, consists of 3 people, then all of you 3 present part of the research. So you're going to explain the problem, You're going to explain what you investigated, and you're going to explain what you obtained. And then, after your presentation, there can be a discussion with the whole group. Yeah, at least there will be questions from other groups. Why did you do this? Did you consider this? Why are you doing this? I don't understand this step. Can you explain it? Yeah, and that's also part of the training. What you usually have when you're doing research, you have to present the results. And it's only nice to talk. Don't worry about people are looking at me, how I move, because usually you're not doing that. Yeah, if you think you followed the lecture of Ferdinand this morning, did you look? How he was walking, how he was behaving, using his hands. Did you look at that? Most likely not. So most of the students will also not look at you. So a lot of people are very nervous in the beginning to give a presentation, but you should not be. Yeah, just enjoy it. Yeah. Okay, and that's what we will do on Thursday. So then we will have 8 groups that are presenting more or less half an hour with 5 to 10 minutes discussion. So then we have the whole Thursday to discuss all the problems, and then you will also see that how the other students used the methods that we explained not only during this course, but also in earlier courses and your earlier bachelor and master courses. And then you see a nice interaction with all those methods. Okay, I wish you a good weekend. We now have lunch, so yeah, okay, see you next week Friday. Okay, thank you.
Thank you.